This machine was supposed to change everything. A sleek, black wedge that would slice through the atmosphere like a knife through silk. It wasn't just another rocket or another plane. It was something entirely new. Something that would make astronauts obsolete and turn pilots into space warriors. The Boeing X-20 Dyna-Soar was America's answer to the impossible. A spacecraft that could launch like a rocket, maneuver like a fighter jet, and land like a glider. It promised to give the United States total control of space. Military control, strategic control. The kind of control that could end wars before they started. But it never flew. Not once. After 7 years of development, billions of dollars, and the brightest minds in aerospace engineering, the program vanished into classified files and forgotten hangar bays. What happened? Why did the most advanced spacecraft ever conceived disappear just as it was reaching completion? The answer lies buried in Cold War politics, technological ambition, and a single decision that changed the course of space exploration forever. This isn't just the story of a canceled program. It's the story of a future that never was. A future where space belonged to soldiers, not scientists. Where orbit was a battlefield, not a laboratory. The Dyna-Soar was more than metal and fuel. It was a weapon, a symbol, a dream that died in the shadow of something bigger. The spaceplane that almost ruled the stars. In 1957, the world watched as a small metal sphere beeped its way across the night sky. Sputnik had shattered American confidence and triggered a panic that reached the highest levels of government. The Soviet Union wasn't just ahead in space. They were ahead in everything that mattered. Nuclear weapons, intercontinental ballistics, and now the ultimate high ground. Space itself. But while NASA scrambled to catch up with Project Mercury, the Air Force was thinking differently. They didn't want to just reach space. They wanted to own it, control it, turn it into the next frontier of military dominance. The Mercury capsule was impressive, but it was also limiting. Once launched, it followed a predictable path. It splashed down in the ocean like a stone. There was no precision, no flexibility, no real utility beyond proving a point. The Air Force envisioned something revolutionary, a spacecraft that could launch into orbit, stay there for days or weeks, then return to Earth and land on a runway like any other aircraft. It would be reusable, maneuverable, and deadly. This wasn't about exploration. This was about warfare. They called it the Dynamic Soaring Vehicle. Dyna-Soar for short. The concept was audacious. A pilot would sit inside a sleek, triangular craft mounted on top of a Titan rocket. The rocket would boost the vehicle into orbit, then separate. From there, the pilot would have complete control. He could change altitude, adjust course, even rendezvous with enemy satellites. When his mission was complete, he would fire retro rockets, re-enter the atmosphere, and glide to a landing at Edwards Air Force Base. No parachutes, no ocean recovery, no waiting for rescue ships. Just pure military precision. Boeing won the contract in 1959, beating out industry giants like Convair and Lockheed. Their design was elegant in its simplicity, a flat-bottomed lifting body with swept wings and a vertical tail. The entire vehicle was just 35 feet long, but it packed the technological punch of a small city. Advanced heat shields, reaction control systems, and navigation equipment that wouldn't look out of place on a modern fighter jet. The pilot would sit in a pressurized cockpit, protected by layers of specialized materials designed to withstand the hellish heat of re-entry. Unlike Mercury astronauts, who were essentially passengers, the Dyna-Soar pilot would be in complete control. He could manually adjust his flight path, target specific landing sites, or even abort the mission and return to Earth at any time. But the real genius wasn't in the spacecraft itself. It was in what the spacecraft could do. The Dyna-Soar wasn't just a research vehicle. it was a weapons platform, a reconnaissance system, a space interceptor capable of hunting down enemy satellites and destroying them. In the hands of a skilled pilot, it could become the ultimate military asset. The Pentagon saw the potential immediately. Here was a way to project American power into the cosmos, to turn space from a scientific curiosity into a strategic advantage. While the Soviets launched their cosmonauts in primitive capsules, America would deploy space pilots in advanced warships. The balance of power would shift permanently in favor of the United States. But building a spaceplane wasn't like building a conventional aircraft. Every system had to work perfectly in the vacuum of space, the crushing acceleration of launch, and the searing heat of re-entry. There were no second chances, no room for error. The margin between success and catastrophic failure was measured in fractions of degrees and milliseconds, engineering the impossible. The challenges facing the Dyna-Soar team were unlike anything aerospace engineers had encountered before. This wasn't just about making something fly, it was about making something survive. Space is hostile in ways that ground-based testing could never fully simulate. Temperature swings from minus 250 degrees Fahrenheit in shadow to plus 250 in direct sunlight. Radiation levels that would kill an unprotected human in minutes, and the constant threat of micrometeorites traveling at velocities that could punch through steel. The heat shield was perhaps the most critical component. During re-entry, the Dyna-Soar would experience temperatures exceeding 3,000 degrees Fahrenheit. The leading edges of the wings would glow white-hot, while the pilot sat just feet away in his pressurized cockpit. Boeing engineers developed a revolutionary system using molybdenum and graphite composites. These materials could absorb and dissipate the thermal energy without melting or cracking, but the heat shield was just the beginning. The vehicle needed attitude control systems that could function in the weightless environment of space. Tiny thrusters positioned around the spacecraft would fire in precise sequences, allowing the pilot to roll, pitch, and yaw with the accuracy of a fighter jet. The fuel for these thrusters had to be stored in lightweight tanks that could withstand the temperature extremes of space. The cockpit itself was a marvel of miniaturization. Every instrument, every switch, every display had to be lightweight, reliable, and capable of functioning in zero gravity. The pilot's seat was designed to rotate and adjust automatically, compensating for the changing orientation of the spacecraft during different phases of flight. Life support systems had to provide breathable air, remove carbon dioxide, and maintain comfortable temperatures for missions lasting up to 2 weeks. Navigation presented its own set of challenges. Unlike aircraft, which could rely on ground-based radio beacons, the Dyna-Soar had to navigate using stars, planets, and inertial guidance systems. The pilot would need to calculate orbital mechanics in real time, adjusting his trajectory to intercept targets or avoid debris. It was like playing three-dimensional chess while traveling at 17,500 miles per hour. The landing system was equally complex. The Dyna-Soar would approach the runway at speeds exceeding 200 miles per hour, with no engine power and only one chance to get it right. The pilot would need to judge his approach perfectly, compensating for crosswinds, atmospheric density, and the weight distribution of his spacecraft. A mistake would mean death, not just for the pilot, but potentially for anyone on the ground. Testing began with scale models dropped from high-altitude aircraft. These early flights validated the basic aerodynamics of the design, but they couldn't simulate the full complexity of orbital flight. Wind tunnel tests pushed the boundaries of what was possible, generating data on heat transfer, structural loads, and control effectiveness. Computer simulations, primitive by today's standards, crunched thousands of variables to predict how the vehicle would behave in space. By 1962, the program had consumed over $400 million and employed thousands of engineers, technicians, and test pilots. The first orbital flight was scheduled for 1965, with a full squadron of operational vehicles planned for 1967. The future of space warfare seemed within reach, but in the corridors of power, a different conversation was taking place. One that would determine not just the fate of the Dyna-Soar, but the entire direction of America's space program. The decision-makers were having second thoughts. Deep in the Pentagon, behind closed doors where classifications meant everything, and budgets meant even more, a fundamental question was being asked. Was the Dyna-Soar worth it? The program had grown from an ambitious experiment into a bureaucratic monster. Cost overruns were becoming routine. Technical challenges were multiplying faster than solutions, and somewhere in the maze of military planning, priorities were shifting. The problem wasn't just money, though money was certainly a problem. The Dyna-Soar was competing for resources with dozens of other defense programs. Polaris submarines, Minuteman missiles, conventional aircraft, and 1,000 smaller projects all demanded funding. Each program had its champions, its lobbyists, its political supporters. The Spaceplane was impressive, but it was also theoretical. A promise of future capability while immediate threats demanded immediate responses. More troubling was the question of mission. What exactly would the Dyna-Soar do that couldn't be done better, cheaper, or faster by other means? Reconnaissance satellites were already providing detailed intelligence about Soviet activities. Unmanned systems could stay in orbit indefinitely without the weight and complexity of life support. Nuclear missiles could deliver devastating payloads anywhere on Earth in 30 minutes. The Dyna-Soar offered flexibility, but at what cost? Secretary of Defense Robert McNamara was asking hard questions. He was a numbers man, someone who believed that every program should justify its existence with cold, mathematical precision. The Dyna-Soar team had passion, vision, and technical brilliance. What they didn't have was a clear, compelling answer to the question of why America needed space pilots when it already had astronauts, satellites, and intercontinental ballistic missiles. The Air Force pushed back with scenarios that sounded like science fiction. Dyna-Soar pilots would intercept Soviet satellites, disable them, and return to Earth with critical intelligence. They would deploy orbital weapons platforms that could strike any target on the planet. They would establish permanent space stations that could serve as forward bases for military operations. The possibilities were endless, they argued. The strategic advantages were obvious, but McNamara wasn't convinced. He looked at the budget projections and saw a program that would cost billions more before it flew its first mission. He looked at the technical challenges and saw risks that could delay the program for years. Most importantly, he looked at the broader context of American defense needs and saw resources that could be better spent elsewhere. The space race was changing too. President Kennedy had committed the nation to landing on the moon before the end of the decade. NASA was consuming enormous amounts of funding and talent to make that dream a reality. The Apollo program promised to demonstrate American technological superiority in a way that would capture global attention. It was peaceful, inspiring, and politically powerful. The Dyna-Soar, by contrast, was military, secretive, and potentially provocative. There was also the question of international perception. The world was watching America's space program with a mixture of admiration and concern. NASA's civilian missions were seen as scientific achievements that benefited all humanity. The Dyna-Soar would be seen as the militarization of space, a step toward orbital warfare that could trigger a new arms race. At a time when the Cold War was already pushing the superpowers to the brink of nuclear conflict, did America really want to open another front in space? The pilots didn't see it that way. They saw opportunity, adventure, and the chance to be the first warriors of the space age. Test pilots like Neil Armstrong, who had been selected for the Dyna-Soar program, understood the risks but embraced the challenge. These were men who had spent their careers pushing the boundaries of flight, breaking barriers that others thought were unbreakable. The Dyna-Soar represented the ultimate test of pilot skill and courage, but even the pilots were beginning to have doubts. The program had been promising orbital flights for years, but the actual hardware remained frustratingly elusive. Wind tunnel tests were one thing. Actually, strapping yourself to a rocket and riding it into orbit was quite another. The Mercury program had already demonstrated that human spaceflight was possible, but those flights lasted minutes or hours. The Dyna-Soar would require missions lasting days or weeks, with pilots performing complex maneuvers in the hostile environment of space. The technical challenges were mounting faster than the solutions. The heat shield materials were proving more difficult to manufacture than expected. The control systems were heavier and more complex than originally planned. The life support systems required constant refinement to ensure they could function reliably in zero gravity. Each problem that was solved seemed to reveal two more that needed attention. Boeing's engineers were working around the clock, but they were fighting physics as much as they were fighting deadlines. The fundamental laws of thermodynamics, orbital mechanics, and materials science didn't care about political pressure or budget constraints. The Dyna-Soar would work when it was ready to work, and not a moment before. By 1963, the program was at a crossroads. The first unpiloted test flights were finally scheduled, but they had already been delayed multiple times. The full operational capability that had been promised for 1967 was looking increasingly optimistic. Cost estimates were rising, technical risks were multiplying, and political support was wavering. In the broader context of American space policy, other programs were showing more immediate promise. The Gemini program was preparing to demonstrate orbital rendezvous and long-duration flight. Apollo was making steady progress toward the lunar landing goal. Military satellites were providing reconnaissance and communications capabilities that were both effective and affordable. The Dyna-Soar was beginning to look like an expensive solution to problems that were being solved by other means. The final blow came from an unexpected direction. The Soviet Union, which had been the primary justification for the program, was showing little interest in developing similar capabilities. Their space program was focused on spectacular firsts and propaganda victories, not on practical military applications. If the Soviets weren't building space fighters, did America really need them? The writing was on the wall, but the engineers and pilots working on the program couldn't see it yet. They were too close to the technical challenges, too invested in the solutions they were developing. They believed that the next test, the next breakthrough, the next milestone would vindicate their efforts and prove the value of their work. They were wrong. The decision had already been made, not in the laboratories or test facilities, but in the budget meetings and policy reviews where the real power resided. The Dyna-Soar was about to become another casualty of the Cold War, a victim of changing priorities and political calculations. The future of space warfare would have to wait for another day, another program, another generation of dreamers and engineers willing to push the boundaries of what was possible. But for now, the spaceplane that was supposed to rule the stars was running out of time, the program that wouldn't die quietly. December 10th, 1963. The date that should have been just another Wednesday became the day that changed everything. Secretary McNamara walked into a conference room filled with Air Force generals, Boeing executives, and NASA officials. The meeting was supposed to be routine, a quarterly review of program progress and budget allocations. Instead, it became an execution. The numbers were damning. The Dyna-Soar had consumed $410 million and hadn't put a single pilot into orbit. The first unmanned test flight, originally scheduled for 1963, had been pushed back to 1966. Full operational capability, once promised for 1967, was now projected for 1969 at the earliest. Meanwhile, the Soviet space program was launching cosmonauts with increasing frequency, demonstrating capabilities that the Dyna-Soar was still years away from matching. McNamara didn't mince words. The program was being terminated immediately, not suspended, not restructured, not delayed, terminated. The contracts would be canceled, the facilities would be closed, and the resources would be redirected to projects with more immediate military value. The room fell silent as the implications sank in. 7 years of work, thousands of careers, and America's most ambitious space project were ending with a bureaucratic pronouncement. But the Air Force wasn't ready to surrender. General Curtis LeMay, the legendary bomber commander who had helped win World War II, stood up and delivered a passionate defense of the program. He spoke of strategic advantages, of the need to control the high ground of space, of the folly of abandoning such an advanced project when it was so close to completion. His words carried the weight of decades of military leadership and hard-won victories. It didn't matter. McNamara had made his decision based on analysis, not emotion. The Dyna-Soar was a luxury that America couldn't afford, a technological marvel that served no clear military purpose. The resources would be better spent on the manned orbiting laboratory, a simpler space station concept that could provide reconnaissance capabilities without the complexity of a reusable spaceplane. The pilots took the news hardest of all. Neil Armstrong, who had been selected to command the first orbital mission, watched his dreams of space combat evaporate in a single afternoon. Chuck Yeager, the first man to break the sound barrier, saw his hopes of breaking the space barrier crushed by political calculations. These were men who had spent their lives pushing boundaries, and now the ultimate boundary was being declared off-limits. Boeing's engineers were devastated. They had solved problems that had never been solved before, created technologies that wouldn't be seen again for decades. The heat shield materials they had developed would eventually find their way into the Space Shuttle program. The control systems they had designed would influence every subsequent spacecraft. The aerodynamic principles they had mastered would shape the future of hypersonic flight. But none of that mattered in December 1963. The Dyna-Soar was dead, and with it died America's first serious attempt to militarize space. The program that was supposed to give the United States permanent dominance over the cosmos had become a cautionary tale about the dangers of technological ambition exceeding political will. The aftermath was swift and brutal. Within weeks, the test facilities at Edwards Air Force Base were being dismantled. The prototype spacecraft, nearly complete after years of painstaking construction, was cut up for scrap metal. The specialized equipment worth millions of dollars was sold off or transferred to other programs. The institutional knowledge, accumulated through years of trial and error, was scattered to the winds as engineers and technicians found new jobs with different companies. Some of the personnel were absorbed into NASA's growing Apollo program, where their expertise in high-temperature materials and life support systems proved invaluable. Others went to work for defense contractors, applying their space-age knowledge to more conventional military projects. A few tried to keep the dream alive, proposing smaller, cheaper versions of the Dyna-Soar that might attract renewed interest. But the political climate had changed. The Cuban Missile Crisis had brought the world to the brink of nuclear war, and both the superpowers were beginning to realize that space might be better left as a peaceful domain. The Outer Space Treaty of 1967 would formally prohibit the deployment of weapons of mass destruction in orbit, effectively ending any chance of reviving the Dyna-Soar concept. The irony was bitter. Just as the program was being canceled, some of its most challenging technical problems were finally being solved. The heat shield materials had passed their most rigorous tests. The control systems were functioning flawlessly in simulations. The life support systems had demonstrated their ability to sustain a pilot for extended periods. The Dyna-Soar was closer to reality than it had ever been, but reality was no longer relevant. In the classified archives of the Pentagon, thick folders full of test data, design specifications, and operational plans were stamped with security classifications and filed away. The knowledge that could have put armed pilots into orbit was buried beneath layers of bureaucracy, and forgotten by all but a few dedicated researchers who would occasionally dust off the files and wonder what might have been. The Soviet response to the cancellation was telling. Instead of celebrating the end of an American military space program, Soviet officials seemed almost disappointed. They had been developing their own spaceplane concepts, partly in response to the perceived threat of the Dyna-Soar. Without an American program to compete against, their own military space projects lost much of their urgency and funding. The space race continued, but it had fundamentally changed character. Instead of being a competition between military space planes, it became a race to the moon between civilian space agencies. The focus shifted from orbital warfare to scientific exploration, from military dominance to peaceful cooperation. The Dyna-Soar had been designed for a different kind of space age, one that never came to pass. Years later, when the Space Shuttle program was being developed, NASA engineers would quietly retrieve some of the old Dyna-Soar files. The thermal protection systems, the landing procedures, the pilot training protocols all contained valuable lessons for the new generation of spaceplanes. But the shuttle was designed for peaceful purposes, for launching satellites and conducting scientific experiments. The military applications that had driven the Dyna-Soar were carefully excluded from the new program. The legacy of the canceled program lived on in unexpected ways. The pilots who had trained for space combat became the first generation of NASA astronauts. The technologies that had been developed for military purposes found new applications in civilian space exploration. The manufacturing techniques that had been pioneered for the Dyna-Soar influenced the construction of everything from commercial aircraft to nuclear submarines. But perhaps the most important legacy was the lesson learned about the relationship between technology and politics. The Dyna-Soar had been a triumph of engineering, but it had failed as a political project. It had solved technical problems that had never been solved before, but it had failed to solve the fundamental problem of justifying its own existence. In the end, the most advanced spacecraft ever conceived had been defeated not by the laws of physics, but by the laws of bureaucracy. The dream of space warfare didn't die with the Dyna-Soar, but it went underground. In the decades that followed, military space programs would continue, but they would be smaller, more focused, and more carefully hidden from public view. The age of the spacefighter had ended before it had truly begun, leaving behind only blueprints, test data, and the haunting question of what might have been. The black triangle that was supposed to slice through the atmosphere like a knife through silk had been relegated to the realm of what-if scenarios and alternative histories. But the engineers who had designed it, the pilots who had trained for it, and the officials who had canceled it would never forget the brief moment when the future of space warfare had seemed within reach. The Dyna-Soar had been more than a machine. It had been a symbol of American ambition, a testament to the belief that any technical challenge could be overcome with enough determination and resources. Its cancellation marked the end of an era, the moment when the space age discovered its limits and chose a different path toward the stars.